I'm very happy that we're all together here to talk about urban metabolism. It's something that I've been researching for the past 5-6 years now, and it's now getting momentum, and something that it really could make a difference. I'll just answer those two questions, which I think are really the introduction for this, is what it is, and then the most important question, why is it relevant? As Ulf mentioned, I'm doing now postdoctoral research in Brussels and in Paris, and the last little logo over there is Metabolism of Cities. It's a initiative, online and open source initiative that we created now. It's been a year. Before it was called something else. We've been working on this voluntarily about how to promote urban metabolism. We collect many publications inside of that. We try to have many useful data that you can find inside. Just go metabolismofcities.org. So what is urban metabolism? Let's start very simply. It generally starts with the analogy of living organism and a city. This metaphor is more an exercise. It's more something that we use to think about cities. There has been many criticism about using such metaphors to compare cities as organisms, because cities are much more complex than a cell. I'll go through it, but that's the basic. That's what urban metabolism is. It's a comparison between a living organism and a city in the way that it needs resources to function, and then during its functioning it produces wastes or things that go out of the system. Now the story goes back to this bearded guy. He's very well known. Back in the capital, when he wrote that in the 19th century, he already started talking about urban metabolism as the interaction between society, technology, and the capital. This metaphor has been used profoundly and profusely. It's here in the 1920s, you see the Chicago School of Sociology. It was used by Park as the metabolism was the pulse of the city. Over here, this is Chicago, and this loop system. The metabolism was how residents were going from one class to another and to another, were pushed outside of the loop. And then there were other people in between those two, but the major person that coined the metabolism of cities was Abel Woolman, and in '65 he was a sanitation engineer. That's where, let's say, the scientific and environmental assessment part of urban metabolism came together. Before it was how the city was working. Now it was how the city, what are the flows that come inside of the city, what are the flows that exit the city. Then you had, in the 70s, a bunch of ecologists that found this metaphor quite useful. It was urban ecosystem, not urban metabolism, and it was quite interesting for them. There was a lot of money from UNESCO and the Man in the Biosphere program. They wanted to compare actually a city to an ecosystem. It was something worth mentioning and worth studying. It's a different type of ecosystem, but still an ecosystem. Over there, probably, if you know urban metabolism, you definitely know this illustration. Duvigneau, back in the 70s, he was a botanist and an ecologist in ULB, in Université de Brussels. He studied the ecosystem of Brussels already 40 years ago. It has its limitation. We won't go into the details. I'm glad if we do, but I don't think we have time. On the top, you have Hong Kong. So in the 70s, late 70s, there was a big interest into that movement. 5-6 studies started, and then nothing. For 20 years, big criticism. This cannot be done by engineers. This should not be done by chemists. They don't understand the city. They want to reduce society into flows. This is a disaster. A lot of criticism, nothing happened. And then late 90s, beginning 2000, you had a big movement until today. Now you have 200 plus, 300 plus studies across the planet on urban metabolism. There are many streams in urban metabolism. I will not go, I'll mention them in a bit, but over here, it's a bit cropped, but it doesn't matter. You see just how many studies are across the planet. Go on metabolismofcities.org, you'll find them. But then, as I said, there are many ways that urban metabolism is used nowadays. It's done, first of all, as a system-based approach to understand the city, of flows that enter and exit. It's used by environmental administrations to monitor the city and do this across time in order to keep track if we're addressing the environmental issues, the pollution, emissions, and all that. It's used in political ecology as a way of how society is colonizing environment, or how the different elements are have repercussions in social classes and all that. Also complex modeling. Anyhow, what's important for us now is to consider cities as systems. Systems that have also subsystems, but also have feedback loops and have flows. This is the important thing to understand. If you look at the 300 plus studies that exist nowadays from 2000 to today, what they do with urban metabolism is just this, a large collection of data. They have data and the inputs, energy, water, materials, data at the outputs, CO2 emissions, wastewater, export materials or waste, and they have data for inside. What's inside is the material stock, is what's around us, all the materials that are around us. Generally, that's it. An urban metabolism study is you take a pen, you just look on websites, and you just fill all of these categories. Now, it's a bit more complicated than that. The exercise, that's it. If you have Brussels, you put numbers, that's it. So we can say, for instance, it's 250,000 of millions cubic meter of water per year in 2011. That's a lot of water. But what does it mean? Well, what do we understand with these figures? If we do it per day and per person, perhaps it talks to you more. For instance, it's 150 liters per day per person. But then, so what? Is it a lot? Is it not? Why do we care about these figures? And that's why is it relevant? Why do we talk about urban metabolism? Because urban metabolism is about accounting, but once you have this accounting, you can do many other things. We all know it. Urban areas are the focus of urban environmental issues. First of all, because they occupy so little space, and yet they host half of the population, and in the future this will increase to, in 20, 30 years, this percentage will increase to 3/4. And nowadays they consume around 3/4 of global energy and produce 3/4 of greenhouse gas emissions. So urban areas are really something we should study. It's also, as I said before, on the left you have urban population, on the right you have rural population. What you see on the right is that it's now stagnating a bit, and on the left is keep going up and up again. And most importantly, in gray over here, you have Asia. Down in orange, you have Africa. New cities are getting built every day. So it's not only about cities that exist, but also cities that will exist, that urban metabolism can help us about. And then, to really understand why cities are so important about urban environmental issues, is over here you have, for the last century, the global material consumption. What you can see almost in the middle, in the 50s, after Second World War, our material consumption really went up. Before that, it was really stable. And on the left, you have the absolute of all the words. On the right, you have per person. So if you look at the right, the orange, which is the biomass, the amount of food that we get, it's stable. Alas, for the last century, it's stable and then goes a bit down. So as persons, we consume almost the same amount of food if we take the whole population of the planet. Now, whatever is on top is energy, construction materials, and metals. So you see that What's happening is all of them are increasing. This is increasing because new cities are built and because we need materials to keep our cities running. We don't need materials for us. We need for our cities. This, of course, is important. These are the 9 planetary boundaries, and we have already surpassed 3 of them, I'm sorry. And over here, the green, you see that we are going to cross the tip already of some of them. So we are already changing ecosystems. We are changing biodiversity across the planet. Because of the food system that we have, we consume too much nitrogen, and oceans have too much nitrogen in them. So we really have an impact on the planet, and cities do have an impact on the planet. Now, how to reduce them, you might ask? That's the most important question, right? We want to measure them in order to reduce them. Now, if you're following what's happening, a lot of things are happening, a lot of money is they put effort to reduce that for cities, for nations, but cities seem to be the #1 place to start. Most of the actors don't know how to do it yet. Cities are trying to do, to help go to the 1.5 degrees, but we don't really know how. There is a lot of institutional push to do that. Now, how to reduce them? For the relevance until the end, I'll give you 3 hints of why is it relevant, why urban metabolism is relevant. The first one is to identify drivers of consumption, drivers of pollution. This is the #1 relevant piece that I will really spend some time, and then there are 2 others. So identify drivers. How to measure who is responsible? Well, over here you have 3 types of territories. Top left, territory A; right, territory C; top bottom, territory B. On the right, you see territory C. What you see are many flows around. You see flows that are going to other territories. So let's say territory C is a producer. Shenzhen in China is one of the biggest manufacturing cities in the world. But all of its products are not there for its inhabitants. It's there for the other inhabitants of the planets, for the consumers. Now, let's take territory B, bottom left. Let's say territory B is Copenhagen. It has, over there, it has renewable energy. It's very green. It doesn't produce anything on its territory. It seems to be a very, resource efficient city. However, it's reliant to territory A and territory B in order to exist. So who's responsible? Is it the producer or the consumer? And how do we measure this? Well, how do we measure this? As I said before, urban metabolism is a combination of data, of inputs and outputs. Sometimes we also take into account the stock. But we have inputs and outputs. So what? How do we know how to reduce those inputs and outputs? There are 3 ways to do that. Part 1 is temporal evolution. So we look at today. Let's say Brussels consumes that much energy and produces that much greenhouse gas emissions. But was that the same amount yesterday, and will that be the same amount tomorrow? Well, if we plot this, if we have the inputs and the outputs across time, then today is over there. But then if you really take data for all of the years until today, then you see that they have different patterns. These are not the results of Brussels. This is an example, but I'll go to the results of Brussels in a moment. And what that says is that at different moments, you have different inputs and different outputs. It also means by knowing if it's more inputs than outputs, your city might be growing. If it's more outputs than inputs, perhaps your city is shrinking. If it's the same, perhaps you have a very linear system where whatever comes in goes out. So the temporal evolution of your urban metabolism is something that allows you to understand technological change, behavioral change, systemic change inside of your economy. Temporal evolution can tell you a lot of things. For instance, here we have Brussels. there are some characteristics of Brussels. The top two are climate. You see that across time, they go up and down. There's no big trend. These are the 40 last years, sorry, from 70s to today. And then you have inhabitants, which makes this small little U. From the 70s to today, it went back down to 90s and then up today. And then you have a bunch of other indicators. You have vehicles, number of houses, number of buildings, expenditure, average income, all that is going up. So at the beginning I was thinking, if inhabitants are doing the U shape, so should every other indicator, right? But no, everything is going up except population, so something doesn't feel right. When we look at water consumption in Brussels, this is from after Second World War to today, what you can see that's actually going up until today, and around 2000 until today is stabilizing. So you remember, population is doing a U shape, but water consumption is going up. So it's not population that's driving water, right? And then this is electricity. Electricity doesn't have the same pattern. It goes much more rapidly up and then stabilizing. So again, population is changing. It does a U shape, but this doesn't reflect the same shape, the same curve. So over here on the left I have energy, and on the right the previous indicators I showed you. You have electricity, natural gas, petroleum products. Well, you can see that electricity seems to be very much related with the other urban indicators. Natural gas perhaps also. Petroleum products not at all. And then if you do it by sector, you see that industry is going down, tertiary is going up. So you don't really see a big relationship. You don't know what's driving metabolic flows, right? It's not that easy. So that was one way to look at how to identify drivers. There's a second way to identify drivers, the spatial way. You can do a spatial analysis. Generally what we do, what we did with OVAM and what I did with a previous study is we look at Brussels as a metropolitan area or as a region. We generally look at where we have data. That's the scale we look at. But anyhow, we look at a scale, but that's one scale. It tells you one reality. It tells you it's 250 million cubic meters in 2011. But you don't know what causes that. If you zoom in, again, this is just an example, you see a different reality. You see that actually that your city is not homogeneous. Some parts of your city consume more than other parts. And that, if you zoom further in, you see that even further some other parts are consuming. And by knowing which parts are consuming, now you can start understanding who's consuming, how they consume, why they consume, etc. Now, in Brussels, you have many spatial scales. You have the metropolitan area on the left, as we discussed. You have the regional scale. So over here, this very small bit, that's the region of Brussels. And then the huge circle around it, that's the metropolitan area, which is 30 times bigger than actually the region of Brussels. And then if you zoom in, you have 19 municipalities in Brussels. You have 145 neighborhoods and 724 statistical sectors. These, by the way, are statistical spatial divisions. They do not physically exist, but there are different spatial scales. And you can imagine that if you zoom in, you'll find out different things. Now, that's again a way to understand Brussels. These are 5 urban indicators of Brussels: population on the left, population density, average income, average dwelling area, and office space. So what do we understand with this? There are 2 very important things that you can see here. First of all, if we look at the municipality, so the top row over here, you can see that there is no big relationship between, let's say, population and average income, or with office space. There doesn't seem to be something, and it's the same for all of the scales. The second thing that you can see is that, for instance, average income and average dwelling area seem to have a relationship over there. And if you zoom in, you're gonna see that this relationship is actually confirmed with different scales. Now, the third and last thing that's important to see here is that, for instance, Uccle, which is this municipality here, it's, I think, number 4 or number 5 in terms of population in Brussels. It's a very populated municipality, right? Actually, if you zoom in, you see that a big part of it is here, is Bois de la Cambre and Forêt de Soigne, which is inhabited. So it means that it's small parts of the municipality that are inhabited. All the rest is empty. And if you zoom in furthermore, you see that it's actually this specific part of the municipality that hosts most of the inhabitants. So you have a reality, and the more you zoom in, the more you understand this reality. And the same goes for the other indicators. What does happen when we zoom in on metabolic flows? We talked before about water, energy. Now I have water, electricity, and natural gas. And this is a very important thing that I'd like to underline. On the top, I have the absolute consumption. So what we read in our meters in our home, if we add them all up, that's what it shows. What we see here is that the distribution of water consumption, electricity consumption, and natural gas consumption seems the same. So in all of the municipalities, they consume in the same way electricity, natural gas, water. Now, if you go down of one row, that's per inhabitant. That's another metric of the same flow. So the flow is water, it's energy, but it's a different way to look at it. Before it was absolute, now it's per capita. Per capita could mean that it is the behavior of persons. So per person, how much you consume, not if we add all of us up. So per person, you see that there is a different distribution between the top row and the middle row. For instance, in natural gas over here, I'll show you just here. On the bottom of Brussels, you have perhaps the most wealthy municipalities, and natural gas could mean heating. So these most wealthy parts of Brussels heat their big houses more. That's what perhaps it says here. Again, I'll show you after that it's not what it says. It partly says that, but it doesn't say that. Then on the bottom, you have per floor area. So number of resources used per square meter. Again, you see a different distribution than the top 2 rows. What it says here, per floor area, it means how efficient are your buildings. Are your buildings old? Are your buildings overpopulated, less populated? This can inform you about that. And you see again that there are other municipalities that are highlighted, more on the west side of Brussels, which is an older, more industrial, and more poor neighborhoods of Brussels. So again, depending on the metric and indicator that you look at, you see a different reality of your flows. And when someone says reduce energy, you might want to understand how and by what type of energy do we talk about. And then from a spatial point of view, when you try to look at urban indicators and metabolic flows, well, you know, most of us say that if we build more dense cities, we'll reduce our energy use or our water use, right? Well, this doesn't say that. If we compare density in Brussels and natural resource use, this is not shown here. We might say, I thought that at the beginning. It was a belief that perhaps richer people would consume more. Again, we don't see any relationship between those two. Office spaces, we have plenty of them in Brussels. If we have more office spaces, then we should consume more. Not really. However, the number of buildings is very much correlated with everything. Now again, remember, this is absolute consumption. This is not per inhabitant, this is not per total floor area. These relationships change depending on the metric that you consider. I don't show you that here because it will take too much time, but this I found over and over in other cities. This is Melbourne, for instance. This is water use in Melbourne. In Sydney you find the same, in Milan you find the same. So the same complex relationship, you find it over and over. There is no one indicator that you might say, oh, that's it. If we do that, we can reduce it. It's not that easy. Now, how to reduce part 3? This is the different types of assessment that you can do. There are 2 types of assessment. It's called the territorial approach and it's called the consumption approach. Territorial approach is what I did so far. What I showed you so far is you draw a line and you measure whatever comes in, whatever goes out. You put meters in those, in each of the flows, and you just measure. That's most of urban metabolism studies. Now you have the right, which is consumption approach. That's a completely different way to see things. Consumption approach is not what comes in your territory. So on the left, it's regardless if it's for production or consumption. We don't care, it just comes in your territory. On the right, it's just because we consume it. I'll take, well, no, that's too simple as an example. The computer. The computer weighs 1 kilo. It's plastics, metals, ores, very, let's say, valuable materials. When I measure it with the left approach, it's 1 kilo of materials entering in Brussels. If I measure it on the right approach, consumption approach tells you, links all the global supply chain that have existed. So how much water did we need to actually extract the petrochemicals that were used for those plastics? How much water was it used to extract those metals? How much water was used during the process of these metals? How much water was used to feed the people that were actually extracting those metals? And you can go like this in an infinite base of their global supply chain in order to understand how this 1 kilo of materials actually has a big impact as energy, water, and materials, much more than this 1 kilo. I'll give you an example. This is Brussels. On the left is the figures I showed you at the very beginning, you know, this linear flows of Brussels. So you have figures, and this is the territorial approach. So you draw a line, you count how much goes in, how much goes out. On the very right, you have the consumption-based approach, which means, remember, how much materials, how much energy, how much water is used for all of the supply chains in order to make this computer. Well, it's actually, for energy, 3.5 times more. So we consume outside of Brussels 3.5 times more energy than how much we consume inside. For water is 42 times. For materials and greenhouse gases, it's also 3.5 times. So if you want to reduce, let's say, water use in Brussels, where do you start? Do you start by closing your tap, or do you start by changing the foods that you eat, because that's what's causing this water dependence? Again, this is a way to think about how to identify drivers, how to reduce our consumption. This was the third and last one. Just as an example, this is where Brussels gets its metals from. The small, very small dot in this map actually mobilizes that much kilotons of metals across the planet. And the second exporter is Australia, importer, sorry. So us, the little dot over there, mobilizes resources from all around the planet just for this computer and everything. So that was the first part of why is it relevant to talk about urban metabolism. It's to actually identify drivers, how to reduce our environmental impact. The second part of why is it relevant to talk about urban metabolism is to cycle material loops. How to go from a linear to a circular metabolism. As you see here, it's very much linear. We get resources, we dump our waste, that's it. Only 3% of our energy is actually produced in the territory of Brussels. Around 3% as well of water is harvested here and of our total consumption. The only energy that we get is from incinerating waste. So, and a slight bit of renewable. So if we talk about circular economy, then we have a lot to do. So why is it important to cycle material loops and how to do it? Again, I'll just borrow some results that we did back in Melbourne. This is Melbourne. On the right, you see, again, it's cropped. Anyhow, you see the material stock. So again, as we said, all the materials that are inside of a city. You can measure it, you have a number of tons. Again, you have to remember that those materials are not just tons. To make these materials, you need energy, you need water, you need greenhouse gas emissions. So you could think as your city as a stock also of resources that have been either wasted because you will just throw away these materials, or you could conserve them. All of these are embodied environmental impacts inside of your city. And by using the existing materials, this is how much you would save. Because if you replace it, then you just need all over this energy. You can zoom in and find out different type of materials. And this is really important for what we call urban mining, so knowing where are materials and when to harvest them. With this, we can know every year how much materials will go outside, where, and how can we harvest them. By doing this, we can, of course, cycle the loops, reduce our embodied environmental impacts. Now, on the right, it's a bit funny, it's carpet. Who cares about carpet? Well, it's important because carpet is over here, flooring. So you see in material terms, here we did the hypothesis that every year we change what needs to be changed in Melbourne until 2100. So if we maintain the same buildings that are today in Melbourne, and every 20 years we change the flooring, every 30 years we change the doors, every 40 years we change the glass, well, that's a bit the distribution that you get. In materials, you can see here what's the most present here are foundations, are slabs. These are the most intense parts of your city in material terms. And flooring is here. This is just a small bit. If you look at the environmental impacts of this, the embodied impacts of energy, water, greenhouse gas emissions, well, this is flooring. This is carpet. So just because you just change carpets, carpet is actually very water intensive, energy intensive, greenhouse gases emissions intensive. So something that doesn't matter in terms of matter actually matters in other ways. So stupid things like carpet can have a huge environmental impact in cities. And if we know when we're gonna change them, that's a big plus. This is for another study I did for Brussels when we did a first urban metabolism study a couple of years ago. We tried to map the number of office furniture that exists in Brussels. There's around 500,000 desks in Brussels, also chairs and storage, etc. So around 24,000 of them is replaced every year. You can see where. And if a quarter of this is sold at a third of the original price, you could get something like 9 million euros per year. So that's just for the furniture, and that's if you sold one fourth of it. You can do the same exercise. Well, it's not as visually appealing, but this is for the technical infrastructure in office space. So all the ventilations, all the toilets, all the lifts, whatever is technical in office spaces. Well, if you do the same exercise, so you sell 1/4 of it at the 1/3 of the original price, you get around 12 million euros per year for Brussels just. A very underestimated guess is around 70 jobs per year. If you are less cautious, it's about 200 jobs per year. For the last case, it was 55 jobs. If you're conservative, it's around 130 jobs if you're generous. So that was the second relevant point of why we need to discuss about urban metabolism. Then third and last, and I will not dwell upon this, is to model future impacts. We need to understand not only what happens today, but also what will happen tomorrow, and how our decisions of today will impact tomorrow. This is one other project we did that finished last year. It's called B-Cube RetroTool. It's about how to retrofit the building stock of Brussels. And in that, we had different spatial scales. We went from the city to the municipality, to the neighborhood, to the city block, to the building itself. And inside of that, you could actually change. Let's say you choose to put 20% more insulation today. What's the impact on energy in 10, 20, 30 years? What's the impact on embodied energy of this? And you could also do that gradually. Let's say 10% this year of double glazing, 20% of next year insulation, and you see the combined effects on this. And this is very useful for strategies, for portfolio management. Let's say a government, they're interested in their money, how to invest their money. Well, you can have some scenarios about which is the best retrofitting strategy for this. I won't go into many more details. I'll just conclude with this. So why is it relevant? It's relevant, first of all, for policymaking, and not fragmentary policymaking, but something that looks across many flows and many spatial scales. Because if you implement something on one spatial scale, it has an impact on another. And you have to think at them at the same time in order not to do a bad decision at one scale for another. These are some of the studies, for instance, that use the metabolic approach to do policy making here in Brussels. And for me, what's important and what we should maintain from this discussion and from urban metabolism is that we need to understand, to take into account more the complexity of the city, because the city, we don't really grasp the whole complexity and what are the levers to diminish our environmental impact. There's a huge need for data. Now there's a good and a bad thing about this. For whatever I showed you, there are millions and millions of data points in order to do that. This takes 4 years, at least, to do that. Governments don't have time for 4 years, but they want the results after the 4 years of study. There is a huge need for data, and we need also to know now what type of data we will be asking to constructors, to grid operators, to all of the people who have data. By knowing what we want to reduce, we also can ask to people what data we need to make our analysis. You also need to, and it's very important at this stage, it's a very slow process. Our study with OLV was 1 year ago. It's something that, again, needs to be done, and it's never finished. It's a study that needs to go on for 5, 10 years. You cannot understand your city in 1 year or 6 months. It's something that needs to go on the long run, and it needs to, every year we will understand a new thing and we will fuel our understanding. Also, urban metabolism is just a start. It's just about fueling interdisciplinary work between planners, between environmental managers, between historians, sociologists. This is, nobody can understand this complexity so far. We need to really work on this together. So I think that's it. Yes. Well, questions, not questions right now. Yes.